the good event regarding the webinar series on the air quality management, science and investment for the sustainable development in the Malé Declaration member countries. So today we are very happy to be sharing all together and learning much from the three speakers in the topic of the long-range transport of air pollution and how to build the capacity on the air quality modeling and forecasting. So as many of us already know about the Malé Declaration, which is a short name for the Malé Declaration on Control and Prevention of the Air Pollution and its likely transboundary effects for South Asia, that was adopted at the 7th Governing Council of South Asia Cooperative Environment Program, or RRCAP, in 1998. And we at AIT RRCP, myself, Vanessa Asurapipit, who is now serving as the head of the air pollution cluster in the AIT RRCAP, has the chance to learn much from this activity that was started since 1998 by the initiative of UNEP and the Stockholm Environment Institute all together at the meetings at that time. Anyways, the activities of Malé Declaration has been running among the 8 member countries involving Bangladesh, Bhutan, India, Iran, the Republic of Maldives, Nepal, Pakistan, and Sri Lanka. That has been a lot of activities running over the past 2 decades. Until last year that we have had the meeting again in Bangkok to revive and consider the plan at the next phase. And so at the moment, with the close collaboration with the RRCAP that AIT-RRCAP has, we started together the webinar series, so that we think that after the COVID, seeing that we have many difficulties to meeting in person. So this webinar will be a good way of doing a sort of training, and also the possibility for all the learners and practitioners who don't have to travel far in order to meet in person. But of course, the activities will have to be included with in-person meeting in the future. But for this third webinar that we planned since March, that we have got the first and the second webinar run already, and you can actually check about these activities and the outcome on the website of AIT-RRCAP, and including RRCAP at very soon. So for just to give you a short overview that this program is expected, we hope to enhance the discussion about the air quality modeling. Since the second webinar, we talk about the initial inventory after the opening in the first time. So the air quality modeling is actually a very important tool, so that from the emission, we can link up from the source to the receptor, and which normally reflected by using the ambient air quality monitoring. That will be the other subject to be discussed later on. But for this webinar, we will talk focusing firstly on the modeling, because this is to give the background of how we do this assessment of transboundary transport of the air pollution, and including the possibility to have the regional picture. So these policy scenarios will be very important to support the decision making at all the levels. So this topic is very important, so that all the model applications that has been going on a lot in some of the countries in South Asia will be reviewed, the latest both in terms of research and our policy making support. So we have a chance to learn from 3 speakers that who have kindly agreed to join our webinar today. So I will introduce the 3 speakers, and we'll also introduce the closing remarks that will be given by Professor Ngonti Kim On from our AIT Center for Nexus of Air Quality, Health, Ecosystem, and Climate as well. Okay, so I just starting from talking about that. The first speaker for today is Dr. Bhupesh Adhikari, who is now serving at the Institute for Integrated Development Studies in Nepal. Actually, Bhupesh is a very good friend, and also he has been actually working very hard with development of model application in South Asia. And I'm very, very happy today that he agreed to join. Actually, Dr. Bhupesh Adhikari has been serving in ICIMOD, the International Center for Integrated Mountain Developments, but now he has a very important mandate out there in IIDS in Nepal. And he actually has developed many important tools for the region that we know as the HKH region. And so for his important activities that has been carried out for many of the member countries in the HKH region, the Hindu Kush Himalayan region, including the development of the Air Quality Watch, and which is a dashboard that has been used by Nepal, Bhutan, Bangladesh, and that has included a state-of-the-art 3-dimensional numerical models also. So he's very much he has a lot of experience to share. And the second speaker actually is we plan for have Dr. Sachin Gude, who is working at the IITM, the Indian Institute of Tropical Meteorology in Pune, but because an urgent call, Dr. Sachin Gude has to go to Delhi this afternoon, and he has asked his colleague, postdoc. He has been actually working for many years together in many of the project. Also, Dr. Gaurav Govardhan to join. I hope Dr. Gaurav is already here in the webinar together. Okay, and actually they are running out a very important program for doing air quality forecast for New Delhi, and including research on fog modeling. And so we will hear from the research team in IITM Pune. And the third speaker is Professor Prabir Patra. Professor Prabir Patra is currently a principal scientist and a deputy group leader at JAMSTEC in Yokohama, Japan. And he is also the visiting professor at the Research Institute for Humanity and Nature in Kyoto. And so they have run the very interesting project, Akash, yeah, similar to the Thai word, Akash, yes, in 2023 and 2025. He has completed his PhD in India, but now continue to work very much in Japan after a lot of research conducted, including about the greenhouse gas, and also contribute to the IPCC AR6 report as well. As I mentioned already, that Professor Kim On will, lastly but not least, of course, will give closing remarks for us today. And before we start, may I ask all the speakers to turn on your camera, please? including Dr. Gaurav. Do you mind to turn on just for us to take the group photo for the record? And okay, thank you very much. Okay, and then we will capture the screen. Okay. Okay, that's good. Okay. Oh, but one more time, because Dr. Gaurav already make the background with our, okay, is that good? Okay, okay. That is a backdrop that we share. Okay, thanks very much. And we will then move on to listen from Dr. Bhupesh Adhikari, who is will be the first speaker, and already mentioned that Dr. Adhikari has been working in Nepal and trying to, like linking up the region as well. So he has not only working in equality, but also contribute to the now the 6th assessment report of the IPCC as a lead author in the working group 1 and continue in the 7th assessment report, AR7 of the IPCC as well. And he has a very long experience at studying and got his PhD and MSc in US. And after that, he came home to really working hard for Nepal and the Himalayan region. So without wasting much time, I will ask Bhupesh to please share your presentation. Are you ready?
Thanks, Vanessa. Share the screen. Can you see my screen? So,
Also, just to mention that all the recording will be shared, to all the participants. Okay, I think that's good. Yeah, you just put on full screen.
Okay, thank you, Vanessa. Again, I cannot see the participants, so if there are any questions, I'll take at the end. Thank you, Vanessa. Thank you, RRCAP, for the invitation extended to IIDS and to me to give my perspective and learnings on how to develop modeling capacity in the Indo-Gangetic Plains and Himalayan foothills. And I'll explain why we're talking about that. And, I'll just give a very broad overview on, what I see, not on the technical details of, capacity building, but, more governance and, high level challenges. So again, thank you so much for the invitation. Okay, so what are we talking about? The region, for those of you in East Asia and elsewhere, in case you may be wondering, okay, what is this IGP-HF? In the recent literature that you're hearing all of a sudden, what is this, right? And so the plot on the left here shows global
Bhupesh, your slides are not in full screen, not visible at the audience level. Is it okay?
Okay, hold on. Let me try that again. Okay, because when we share here, the full screen mode, let me share. Is it full screen now? Is it full screen? No.
No. What about Vanessa? Do you see it? How do you see it?
Okay, let me take out my double screen.
You need to swap the view, swap the screen after.
Now, let me do it like this. I'm taking off my bigger screen. Okay, can you see it now, full screen?
That's good.
Okay, so let's begin. Okay, so the slide on the left, the picture, what are we talking about? IGP-HF, yet another acronym in, development. Right? So this slide, which is a bit dated, but still holds true, shows a global distribution of PM across the world, right? And you see here, the highest concentration at what appears to be in the Indo-Gangetic plains, stretching all the way from Pakistan to Bangladesh. This plains, at the foothills of the Himalayas and the Hindu Kush Mountains, where there's a lot of population, high industrial activity and all, shows high pollution levels here. But we've been, in our work here, we've been able to show that it's not just the plains, but the valleys and mountain cities, such as Kathmandu and, other cities in the region, which are equally polluted, right? And here's a picture of the Kathmandu Valley on any given day. And the problem here is if you look at the global aerosol optical depth, which is a proxy for particulate matter, there's this study that showed that, in South Asia, the trends, so the pollution trends due to particulate are rising. So it's not just 1 year data, but, while in East Asia, here, two hotspots in Asia, but East Asia, at least the trend is decreasing. Yes, it's still high in air pollution levels, but one region shows increasing trend, whereas the other one shows a decreasing trend. So you can't manage or you cannot mitigate what you cannot measure. And so you need to first understand, how do we study air pollution, right? And I don't want to go into details because this is really a talk about models and, how do we improve modeling capacity. But in general, you understand air pollution by in situ measurements, stations such as this. In situ measurements could be airborne, where you take air pollution measurement up in the vertical atmosphere. You could do air pollution studies from remote sensing, where you're looking at pollution from the ground to the top of the atmosphere, such as with instruments such as the AeroNet sun photometer here, or looking at the Earth from space, from top down, And then, of course, you can study air pollution using mathematical models, which is the topic of today's discussion. And I'll go a bit more into this. So again, air quality models, some people call air pollution models, some people call CTMs, sometimes I find people getting confused with CCMs, GCMs, what are these, right? And in this intro talk, I don't really want to go into details of all these nomenclature, but there's good, and we'll share the slides afterwards. You can go into these literature and try to understand what the details are. But the point I want to make here is models illustrate the state of knowledge that we have. Right? So we're trying to develop this 3D model. Right? And in that, how complex is the model depends on how much do we know about a particular topic. And in our case, on air pollution, to what level of detail do we have the data or knowledge that we feed into a model and do something useful with it to be able to control air pollution, right? And so, again, the complexity of the model depends on the physics, the chemistry, geography, meteorology, emissions. And so there was a whole webinar, previously with the Malé Declaration series on emissions. Right? And we're talking about air quality models now. Right? And a lot of things we may know from first principles, conservation, mass, energy, momentum, stuff like that. Or we may build our model based on parameterized equations. Right? So we observe certain things, we put a regression line, form correlations, and then based on that, develop our model. So this was a slide that was presented by a friend of mine who was also one of the presenters in the earlier presentation, Saurabh Guttiganda and colleagues. They looked at the literature on air pollution modeling in India. Okay? And in South Asia, India by far has the most advanced technologies and a lot of work going on compared to other countries. Okay? And here's this very interesting graph, and one of the reasons why we're discussing today. And he looked at Scopus, web search, and then showed that if you have certain keywords, the air pollution literature on air quality, air pollution modeling, air pollution observations have been rising since 1980, okay, almost exponentially. But then if you go deeper into it, 63% of these papers are based on observation. And then within, if you account for machine learning, artificial intelligence, and other topics that include observations, that number goes up to 77%. Whereas if you strictly look at air quality modeling or pollution modeling, that number drops down to 6%. Okay, so you can see that there is a huge discrepancy between studies that are coming out of India on air quality, whether they're observation based or modeling, and you can see overwhelmingly 2/3 are observation based. Within the modeling, the group did a deep dive, and then they also put out a table in the same article, and here's the citation for that. They compared results from India and China, and then you look at, say, for example, even within model, okay, within India, 600 papers are using WRF model. If you look at, say, the famous air quality models, WRF-CAM, CMAC, CAMX, the number drops down very high. Only 139 papers out of WRF-CAM, and then a few from CMAC and CAMX, right? And then there's some 2D Gaussian flume models such as AirMod and all that are still putting out papers on literature. So, I mean, the take-home message is, yes, there's a lot of knowledge that's been, being developed in the last 2 decades, but primarily are observation-based. And so the talk of today is, how can we build this modeling capacity? How can we improve not just papers, but mitigation action using models so that we have a cleaner and healthier environment in IGP each year. So that brings me to this question: is that why air quality models? If there's already all these literature and knowledge that's being generated from different sources, do we really need models? So if you think about these 3 different types of techniques that we use to understand air pollution behavior, each of them have their strengths and weaknesses. So in situ measurements, if you look at where you measure something, how representative is that? What I mean by that is, if I measure air pollution in my office building here, does it represent all of Kathmandu? Does it represent Nepal? So it's got a representative problem. Okay? In situ measurements cannot talk about future. Like if I do some mitigation action, what can be the future air pollution like? Okay? And without some sort of model, whether it's meteorology or other models, you cannot really infer about sources and transformations just by doing measurements. Similarly, satellite also, I don't want to go through the list, has their strengths and weaknesses. But again, despite all the uncertainties, all challenges with air pollution models, as Vanessa mentioned in the opening remarks, they do provide a link between emission sources and observations. Because to control air pollution, what you need is reduction in emissions, and then you need to understand, where are these emissions that you can actually control and mitigate. The other nice thing with the models is, without actually emitting or doing observations, you can, based on model, look at future scenarios, and then also carry out what if scenarios, like what if I convert all my diesel buses to electric, how much of air pollution reduction can I get? Things like that. We call those what if scenarios. So clearly, air quality models are also important if we want to reduce air pollution. So I come to the main point in my talk today. Why I feel we have lots of challenges, or why does the evidence show very few model-based studies in literature in South Asia? And so, I mean, the next slide I'll maybe talk a little bit on the technical side, but these are more policy, more capacity-related high-level challenges. So my first, and these are again my personal reflection and based on my experience. In South Asia, I feel the main problem first is internalizing air quality as a serious problem. If you look at, say, the global burden of disease or the AQLI statistics, 8 million premature deaths globally, or how South Asians are losing how many years of their lives. I mean, there are statistics. Those numbers make you feel that air pollution is a very serious problem, and it is. But that's not being internalized in policy circles, or the budget that's being allocated and all that, right? And then again, let me also put a disclaimer here. Some of these challenges, I think in South Asia, India has advanced quite a bit, and a lot of things don't really apply to India. But the other countries, these challenges are very real. For example, modeling centers. We don't have any dedicated modeling center or a desk or an institution that runs, air quality models day in, day out for policy in South Asia, outside India. There's no regulatory policy framework outside India to look at if, say, can you use AirMod in India you can, but like elsewhere, can you use AirMod to do certain things, or can you use WorkCam to do certain things and plan your policy? So first of all, there's no dedicated centers. Second, there's no policy framework that allows governments or planners to use models. And then there's also no role within the CBO NGO community on what they can do on air quality models. And also, in certain places, sometimes, putting out mass communication on days when air pollution is really bad. Again, there's issues related to putting out communication in a lot of the countries. Right? So to me, from a governance perspective, there's huge challenges that need to be overcome if we really want to build modeling capacity. Second, again, modeling to me is a very interdisciplinary subject. Okay? You need meteorologists, you need computer folks, you need physicists, mathematicians, all these different types of people. And so there's a huge HR gap within each sector. But then unless these different sectors come together and work, it's going to remain a challenge, right? And my experience working in the region for long, I feel there's ways to go to improve South-South collaboration. And the analysis that Sarath and team did also showed that there's a lot of collaboration between North and South. So a country in South Asia would collaborate with the global North, but there's very few South collaboration. And until we build this, no one country, again, because it's complex, requires a lot of resources, it's going to be quite hard to develop modeling capacity. And then the other thing is, okay, what are models used for? Operational weather, chemical weather forecasting or pollution forecasting versus, post-event forecasting. Right? So if we want models to be useful to public, we need to do both. And unless you have, and so operational air quality forecasting is a completely different challenge compared to post-event or some campaign mode analysis using models, right? And so we need to think about what is when we say modeling capacity building, what exactly do we mean? And if it means operational modeling for air quality forecasting, we definitely need the previous two. Another challenge I see propping up in the global south is that we are increasingly competing with the global north. As the computing technology advances and models become more complex, and computers become very powerful, you have centers that run global models at resolution of regional models. So if regional centers do not develop their capacity or do not have that infrastructure, I see increasing competition from global north data providers. What I mean by this is you can get your air quality forecast from, say, Google or Yahoo or Copernicus, or even institutions based in US that will provide forecasts for different parts of the globe. And so if the data is already there, there may be challenges from governments in the global south to say, okay, it's too complicated, we cannot do this. Why just not use data and model from elsewhere, right? So to me, I think that's another challenge. And then of course, all these hardware infrastructure, kind of challenges do exist. But for South Asia, we need to think about, East Asia in the last 20 years have developed quite a bit of their modeling capacity. And there's this very famous project called Model Intercomparison Study, Mixed East Asia. It started in 2000, and they've done Mixed Asia 1, Mixed Asia 2, and then now they're planning Mixed Asia 4. So they're already in their fourth phase, whereas in South Asia, we have yet to begin a model intercomparison study. So it just shows how far we are in building this modeling capacity and doing real work using models in South Asia. Again, I used to do quite a lot of work on the technical challenges. Now my work is focusing more on the policy and high-level challenges. So if I need to put in the technical challenges in overcoming how to run regional air quality models, if you look at a data flow chart of a regional model, something like this, how do you get meteorology data for offline chemical data model? How do you get your initial and boundary conditions? Because usually you get these from global models run elsewhere. Again, emission sources. Yes, you can get some anthropogenic emissions in your city or your country using, localized emissions inventory. But then what about dust emissions or sea salt? Those sort of things. Surface properties, again, land use, land cover, or dynamic, say snow covers. These sort of data, again, increasingly high resolution, increasingly complex data information that need to be fed in to have a really good, robust air quality model. Satellite data simulation, again, you can use data from satellite in real time or near real time to input into your model that can give you a very good outcome, right? So there are all these technical challenges. Solutions are there elsewhere. We need to, at some point also deal with this, but I still feel in majority of the countries that I've worked, the high level challenges remain. Again, the frontiers are elsewhere globally. They are already using air quality models at an operational scale on urban scale modeling. These are, sub-kilometer or kilometer scale modeling. People are already using chemical data available from satellite to improve model forecast. Dynamic emissions assimilation as the road traffic, stuff from, like, say, Google traffic or stuff like that, that get fed into models to improve your emissions. In China, for example, they've already started looking at ensemble air quality models because no one model is perfect or gives you the right information all the time. So they've already started looking at a variety of models, ensemble mode, to do probabilistic air quality forecast. And then again, machine learning, artificial intelligence are increasing in exponential scale. And if we're not even running models, how do we catch up with using machine learning and artificial intelligence to improve air quality forecasts? Okay. But again, I mean, these are technical details, but I think again at a very high level, to increase capacity building of air quality modeling in South Asia, there needs to be a demand that is created from governments to use models to help, with policy actions and mitigation. And unless there is demand, models will only remain at a very academic level. And so we need to be working with, say the local governments, regional, provincial governments, and central governments to start using models. Again, why models? Because they are the state of knowledge that we know. We're basically collating all the information that we know about air quality at a particular region, putting it in some equations and then trying to come up with an assessment of a question that we want to answer, right? And so we need to drive this demand. And I was thinking about this webinar. For the Malé Declaration, I was invited in 2017 to talk about this, how can we promote air quality modeling? And at that time also, since then, when I reflect, it's almost 10 years now. And we still are, long ways to go in increasing air quality modeling capacity. So I think, again, yes, parallelly, universities, research centers are running models, but we also really need our governments to step it up and, start building centers and policies around modeling. So with that, I thank you for your attention, and I'll be happy to take any questions.
Okay, thank you very much, Bhupesh, and with your insight and giving us also and like an introduction a little bit, and with I believe that there would be a number of questions. Actually, I forgot to mention that everyone is very welcome actually to drop your question in the Q&A box so that we can ask directly to the speakers. So actually, Dr. Bhupesh Adhikari has mentioned in a very brief way, because he said that he would not like to take so much detail about the previous work that he has been doing, a lot of those, but still, I think what he raised as questions, as suggestions, will be very, very significant to the discussion here. I don't yet see any particular question for Bhupesh at the moment, but he will stay with us till the end, and there can be more of the question. It's a specific way to drop in anytime. Okay, thank you so much, Bhupesh. I will move on, and then we can come back to you again during the Q&A session.
Thanks.
Okay. And let me introduce the next speaker, who has come upon the request of Dr. Sachin Gude, who has initially he has already agreed to really be with us, but because of this urgent matter that is happening out there in Delhi as well, so we have a chance to hear from his team. Okay, and Dr. Gaurav Govardhan is already there and ready to tell us about a number of activities that they have been doing on the development of the air quality modeling and forecasting for New Delhi, India. Actually, Dr. Sachin Gude has been working in, and his team already working in collaboration with INCAR, National Center for Atmospheric Research, for many years back until now in the effort to develop the modeling capacity for the capital city of India, which is a very challenging place to really modeling. And I believe that the team has a lot to tell us, and I would not like to waste much time. So let me ask Dr. Gaurav Govardhan to share your presentation on behalf of the whole team. Thank you very much.
Thank you. Can you all hear me? Okay, great. Let me start sharing my screen. Can you see my screen? Let me go to the presentation and slideshow. Somebody please let me know if you are able to see my screen and hear me as well. Am I audible and can you see my screen in a full screen mode?
Yes, Gaurav, you're all
Yes,
good.
yes, we can see it.
All right, all right. Okay, thank you. Thank you. First of all,
Yes, yes. Your
a
screen is
bit,
good
yeah,
now. Yeah.
all right, okay. So first of
Thank
all,
you.
really sorry that Dr. Sachin could not attend this important webinar because there was some very urgent commitments that he had to attend because there's some urgent meeting to be organized in Delhi and he had to travel there and he's in continuous meetings in the continuous meetings in Delhi. So here I am. On behalf of him, I'm just going to talk about the air pollution or air quality modeling and forecasting system that our group has developed. Of course, a bit more focused on New Delhi, the capital of India, but it's largely it runs over entire South Asia. So before we begin with the modeling, I would just like to throw light upon why do we need an air pollution forecasting system for Delhi? No one would want to. No one probably would need an introduction for this. The air quality indices levels, especially during the October, November, December, Jan periods, in the capital of Delhi, or capital of India, that is New Delhi, go very high, and these values, I'm sure you don't see these values across the globe as often as you see in Delhi. So, for example, if you see month of October, for the last few days, few years, you're seeing October is also getting more and more polluted. Here I show that 2021 to 2025, 26 onwards, you see the air quality index in October getting crossing 300 values. Again, these values would mean different for different countries, but trust me, 300 is a very high level of air pollution, and 400 and beyond that means severe levels of air pollution. And if you see, October has started becoming more and more polluted. November is also actually, you see slightly cleaner Novembers from 2021 to 2022 to 26. You start seeing air pollution or air quality index reducing in the month of November. December, January, if you see more or less, the air quality index have remained more or less the same. But again, all these values, you see background levels themselves are very high. 300, 400 means very high air pollution events. And how has the situation been in terms of air quality days? If you see, more or less, uh, Octobers are again getting more and more polluted, while Novembers are getting slightly cleaner. Of course, when I say cleaner, they are not as clean as uh, middle of an ocean, but if they are cleaner to what they were in the previous years. And December and January, you more or less see a category which has been named as very poor air quality index in Delhi. And the season mean picture looks like this. Overall, across the season, around 50, more than 50% of times, the very poor air quality category stays prevalent. And you have prevalence of severe air pollution events, but of course that's kind of reducing as you have seen in the years. Uh, that's a main trade-off that's been happening in very poor and severe, but all in all, it's a very pretty polluted scene out there. So what do we do? I mean, I don't have to highlight the importance of having an air pollution forecasting system. So sorry, it just got, yeah, sorry. I don't have to highlight the importance of having a revolution forecasting system. So this need was felt back in 2018, and there we came up with this air pollution forecasting system. Again, as already highlighted very well by the previous speaker, the capacity building for air pollution modeling as well as forecasting needs to be actively looked into. And there are very few centers across, basically across some of the South Asia, which run this forecasting setup. So we are one of them. Uh, I would like to touch upon how this forecasting system works. So, and essentially for all of South Asia, we provide air pollution forecast at every 10 kilometer. That is, the resolution of the forecast is 10 kilometers. And we can zoom in to whichever location we want. In this case, I'm zooming into Delhi. So from 10-kilometer resolution to a 2-kilometer resolution over the national capital region, which is including little more districts apart from Delhi. And just over city of Delhi, we zoom into a resolution of 400 meters. So more or less every other neighborhood of Delhi would have air pollution forecast. And again, this is not a standalone computer-based model. It talks to observation day in, day out. It is one of the important aspects of this modeling system is the chemical data assimilation. So data from satellites, data from surface measurements all across India, as well as data from fire activities that are happening across the country of India or the neighboring countries. All this information is assimilated into the forecasting system, and the uh, along with the boundary condition for chemistry as well as meteorology and initial conditions for meteorology from IITM's GFS model, it runs the forecast for entire India, 10 kilometers, and for Delhi with a high resolution emission inventory, which is at right now 400 meters. It runs it for New Delhi and gives provide forecast for next 3 days. A very brief touch to chemical data assimilation. Chemical data assimilation is a very excellent tool to assimilate the observational data into the modeling uh, uh, domain. And in short, what it does is essentially it minimizes or it basically nudges your observation to the modeling side as much as possible. So by taking into account the errors that could be associated with the modeling with the model, as well as taking into account the error that could be associated with the observations. So all in all, the chemical data assimilation utility essentially minimizes this cost function, which basically gives you difference between basically minimizes the error essentially, I would say. And you do it for satellite data, you do it for surface data, you come up with an most optimal initial condition for a model run, and then you start your model simulation, and then you get the forecast. So all in all, this is how the situation been for last few years. We started with a basic setup of 10 kilometers, then we started putting in the assimilation, then we started putting in the inclusion of fire counts, then this assimilation of surface data. We also use deep learning techniques to identify or predict the fires that might happen in real time. Upon that, we also put in high resolution land use, land cover, as well as in the experimental mode, we have also put in the uh, high resolution topography or morphology within the city of Delhi into the modeling framework. I will show some of the results of this as well. And apart from all this, we are now also moving into assimilate not just PM2.5 and AOD, but also other gas phase species like CO from moped and COs, as well as few other gases from the surface network too. And since we know that Moody's is slowly phasing off, we are putting in assimilation from various data sets as well. So all in all, some of the developments that I'll be showing here are highlighted here. Uh, so how has the forecast performance been? The forecast has been decently okay for air pollution episodes which land up in an air quality index of 300 to 400 or slightly below that. So if you see for all these couple of air quality index categories, the model performance closely ends up uh, in the ideal corner of this particular figure. But for all category, I mean, basically, but for air pollution category, which is beyond 400, that is the air pollution episodes, as we call it in Delhi, when air quality index goes beyond 400, we have a moderate scale, I would say. There is scope for improvement on that. And all the development that we are doing currently are essentially, of course, are aimed towards getting this bias corrected. In short, if you look at the evaluation, I won't go into details of this matrices. There are plenty of those, but probably I would touch upon very one important aspect is the false alarm, right? Because uh, it's very important to have a system which provides you as less false alarms as possible. So for now, what we are seeing is for our system gives you roughly 30% of false alarms, especially for the critical category. When I say critical category, I mean that air quality index crosses beyond 400 and it has 30% false alarms, right? Which means that if your system is predicting that it's going to be a severe air pollution day or an event coming up, 70% of times it occurs in that direction. So that is a all in all main take home message from the evaluation point of view. Very importantly, the previous speaker, Dr. Bhupesh Adhikari, also mentioned about a lot of global north countries sharing their data sets to the countries in the global south for now, and for their air pollution forecast. So here is an example of model intercomparison that we have done for this for New Delhi for a couple of years. Here is our WRFCAM based forecast for New Delhi's air pollution, and here is comparison with all other global models or regional models, ML based models, and others forecast for day 1, 2, 3. And I would like to mention that the WRFCAM based forecast, which is really been tuned for Delhi, outperforms all the models which are coming from the European or US based centers. Even ML based forecasting models are coming closer, but of course, still till now, the WRFCAM based forecasts have been shown to be the best. This is a performance index. I'm not going to details of all this, but this is this performance index, which kind of puts together all the statistical parameters. So this is the model intercomparison that we did. Taking, I mean, this is one of the important things that I would like to show in connection with the Akash project. Professor Prabir Patra, we've been in collaboration for this particular activity. So essentially, this activity was involving data assimilation from the low-cost sensor network that Akash project had over Punjab and Haryana, and showing the usefulness of these particular sensors in the forecasting setup. So what we did is, because over this region you have little lesser concentration or I would say population of the CAAQMS, which is measurement networks. So here you have data from the low-cost network. What we did is we tried to assimilate that data into our forecasting system for a particular event which occurred in the month of November 2024. This event was a total surprise for entire Northern India community, all of us, because we had never expected that this would occur, and because of clouding, the satellite data could not give us enough information, and there are hardly any continuous measurement sessions across that part of the of India. So the QPG network helped us, and you could see that assimilation of the QPG network into the forecasting system indeed increased the concentrations, and it indeed helped us. So these are the QPG observations over Delhi during that particular event, and these are CPCV observation, that is a pollution network R observations, and we find that once you assimilate QPG data sets, you get most of the peaks that were seen in Delhi during that day. None of the other data sets give you this particular behavior, of course, but it depends on the error characteristics also. Here we show that the standard error characteristics of QPG network, if you put in, you have lesser scale, but if you put in lesser error characteristics and saying that these errors will reduce in time as you go on development of these sensors, we find that it certainly show some promise. The next thing that we have introduced in this particular air pollution forecasting system is some sort of a decision making ability in this. So what we have done is, apart from giving air pollution forecast, we provide contribution from different districts which are surrounding the city of Delhi to Delhi's air pollution. So what is the contribution from 19 different districts which are sitting in the region which has been named as National Capital Region of India? What is the contribution from all these districts to Delhi's air pollution? That is the question we asked. And can we get that contribution day in, day out? And can we provide this contribution to policymakers? That was the question which was asked 4 years back. And we decided to take it up, and we decided to use the passive tracer approach in WRF-CAM, wherein we spawned tracers for all of the emissions from all of these districts, and also emissions from different emission sectors within Delhi. We decided to spawn tracers, and we decided to get this info. I mean, we eventually got this information from the WRF-CAM, tracer-based WRF-CAM. Here we provided tracers for 5 different aerosol species and 4 different regions. So all in all, if we see, around 95% of the PM 2.5 from the model was resolved using our tracers. That is something I would like to show from this vertical image. Uh, all in all, we put 470 tracers in the model. These are all 3-dimensional tracers. Again, this is all these regions which are marked here were traced, or whose emissions were traced, and their contribution to Delhi's emissions were traced or was given. Apart from this, we also include something called as scenario tracers. What we mean that if any of these emission sources are reduced by a certain quantity, what would happen to air pollution in Delhi? So this sort of a policy level help assistance that was included in this system. So uh, the idea was the policymakers could create their own air pollution reduction scenario by switching off some of the districts and see what are the possible improvements that one would get if those controls are achieved. So so we ran DSS for last few years, and this is the basic main picture that comes out from this something we call as decision support system, or DSS. We say that Delhi's air pollution essentially is a three-way problem, 3 equal contributors, a three-body problem, as people call it. Around 1/3 of it comes from the pollution comes from the city of Delhi itself. Another 1/3 comes from the national capital region, that is the NCR area, which is encircling the city of Delhi. And the remaining 1/3 comes from regions which are not part of NCR, but which are part of, but away from NCR. So this 1/3 rule kind of comes in. That's also main fundamental message comes from DSS. And also you see around 25% improvement would occur if 40% reductions are Delhi and surroundings are done. So this is the kind of information that we provide. And remember, all this information comes from a single model run every day. So policymakers and policymakers sitting in Delhi in the Commission for Air Quality Management have been utilizing our forecast as well as the decision support system to make use of basically to give out there is something called as graded response action plan, GRAP restrictions in Delhi, which get activated based on the air pollution levels and air pollution forecast. So to activate this graded response action plan, our forecasting as well as decision support system has been actively used. But important part is how do you evaluate this source apportionment given by the model? So here is a quick evaluation of this. We compared the model simulated source attribution with respect to measurement-based source attribution for Delhi, and we find that especially for transport sector, our modeled values are roughly in well agreement with the observed values of source apportionment, especially for transport, which is the most important sector as far as pollution in Delhi is concerned. And for other sectors too, for road dust as well as coal and fly ash, you see good agreements with observation-based data sets. So how this system works, we run the WRF-CAM based forecast for multiple resolutions using the chemistry, all sorts of data coming from fires, coming from satellites, coming from inventory. All this data set goes to WRF-CAM along with chemical data estimation utility. We provide not only just a forecast, but also source apportionment, that is region-wise contribution, as well as these reduction scenarios for emissions. What would happen if any of the sources is reduced? And all this information goes to goes to our website, and through the India Med department, it goes to policymakers. And the policymakers sitting in Delhi, like CAQM, Commission for Air Quality Management, Central Pollution Control Boards, and other bodies, depending on forecasts, they take a call if they want to uh, invoke or revoke any of these restrictions, which become more and more restrictive as the air quality index become more and more severe. And if they decide to do so, then the notification goes to close to 150 regulatory bodies in the city of Delhi as well as in the state of NCR about its implementation. So this is how the forecasting activity talks to policymakers and then hopefully the actions on the ground. This is how the loop gets completed. So how do you make use of this utility, the decision support system? One is to estimate the possible effectiveness of the graded response action plan, and we tried to do so wherein we tried to understand if how effective are those restrictions under the response action plan, and we find that the stage 3 and 4 of the graded response action plan could be really effective if it is implemented with a very high level of compliance. We find that around 30 to 40 units of AQI could be reduced by using these restrictions if the compliance is close to 100%. Another way of utilizing the decision support system is to help the commission in coming up with new policies. So here is an example. The Commission for Air Quality Management wanted to see if the agriculture burning activities that are activities happening in the neighboring state of Delhi, that is Punjab and Haryana, if those stubble that is getting burnt, if it's burnt in a controlled condition for heating purposes in industries, coal-fired industries, what would happen to air quality in Delhi? Because on one hand, you are reducing the stubble getting burnt in open, but on the other hand, you are getting it closer to the city of Delhi where you are going to burn, but in a controlled condition. So that question was posed to us by the commission, and we did multiple experiments, and we found that no matter what, if you burn the stubble in a controlled condition, you are going to improve the air quality in Delhi. So based on this analysis and few other things, the Commission for Air Quality Management came up with a directive from there and saying that all the coal-based, coal-fired industries in Delhi should be using at least 10% of stubble for their heating purposes. That was back in 2022. That is something how the system was used by Commission as well. So today we are talking about model development. So I would just quickly talk about the development that we have done in this thing. One is Professor Dr. Adhikari just mentioned about the ensemble-based forecasting system in China. So I would like to mention that we have also done that sort of an study. In fact, just this previous winter, we tested our ensemble-based forecasting system, which is based on the CMAC model. And here is an ensemble made up of different conditions of meteorology. So 21 different ensemble members, which has slightly different meteorology, were put into the model. And the CMAC model was run in 21 different ensemble manner. And we looked at the performance of this ensemble-based forecasting system in terms of ensemble mean. We found that uh, it is comparable with the current dynamical-based forecasting system, but it slightly has higher errors. A, because it's a offline chemistry transport model. B, because it's an ensemble-based forecast without chemical data assimilation. So what we have learned from last year's runs is probably we have to put in the chemical data assimilation for our ensemble-based forecasting system. And that is something which is on our agenda and radar for this year. So here also you can see the ensemble-based forecasting system roughly has comparable accuracy for the forecast for different air quality categories, but slightly has higher false alarm ratio. It tends to overestimate the concentrations a little bit, and because of which you end up having slightly higher false alarms, lesser reduction ability. And current EWS forecast is slightly better compared to the ensemble based forecast, but this is only the first year, so we will improve on that. So the Brier score, which is one of the indices of looking at ensemble purpose forecast, is 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 fairly okay for all the air quality categories I could see here. A value greater than 0.2 is not so good, but only for very poor categories we are 0.31. Again, for severe we are 0.22. So I think we are getting there. We are going to improve on certain aspects. So again, here area under the curve for this particular ROC curves for different categories. If it is greater than 0.7, it's acceptable. For most of the categories, it is greater than 0.7, but for very poor and severe, it's close to 0.7. I think we have to improve on that aspect. Another aspect was to include the missing aerosol species. Today, we are talking about model development. So one of the other development is to, if we can, go-kart scheme, which is currently used in the model, has very crude representation of secondary organic aerosols or in general organic aerosols. So our way of putting in is, why don't we use a more sophisticated scheme? But sophisticated schemes are very computationally expensive. So why don't we use a fast parameterization for that? So here is an example of including a fast parameterization for secondary organic aerosols, wherein the emissions for secondary organic aerosols are derived from emissions for carbon dioxide, carbon monoxide, for different emission sources. For example, transport industries, biomass burning, we identify those particular plumes, and we identify what is the concentration of VOC and CO in those plumes, and from that we invert them back to the ratio of emissions in those plumes, and from those we get emissions for all those VOC species in the model, and we prescribe that to get you the secondary organic aerosols in the model. So this was tried even this year in 2000. Even this year also we tried, in fact, and this is the example of prescription of this fast parameterization of secondary organic aerosol in our scheme. So here is modeled secondary organic aerosols. This is modeled SOA, and what we can do is now we can also disintegrate the secondary organic aerosol produced from different activities, that is transport, then industries, biomass burning, so on and so forth. So this is observed SOA and this is modeled SOA, you can see, and this is the models without the default case of model. So this is the default case and this is the modified way. So you can see we have jumped on quite a bit here. We still have to close the gap. And this is the observed PM 2.5 in Delhi. This is the model PM 2.5 with the secondary organic aerosols fast parameterization. This is without that. So you can notice that with the inclusion of secondary organic aerosols, we are getting closer to this. So again, this is one of the important things to close the gap essentially for the critical event where your SOA formation is probably missed by the model. And this is one of the way of achieving that. Here is a comparison of our newer model with the mosaic scheme, which is the most complicated chemistry mechanism in the modeling scheme in RRCAP. And you could see that if observations are 83 micrograms per meter cube, our model gives you up to 53, where mosaic gives you 62. So we are probably closer to mosaic, not as great as mosaic, but our model runs 5 times faster than mosaic. So that is a trade-off between a much intensive chemistry scheme and a faster but little lesser accurate chemistry scheme. But we are getting there. That is what something I would like to show. Another way of improving the model forecast, especially during extreme events, is inclusion of urban morphology. So here is an example. We took data, high resolution data of land use, land cover, as well as urban morphology from Europe, Sentinel, as well as UT Globus data sets for these regions within the national capital region. What we have done is we have incorporated all these urban fraction, plan area, road density, road orientation, things like that into the modeling framework. And what we find is inclusion of these parameters essentially improve our forecast. So for example, this is a forecast of temperature. This is observed temperature. This is default model. And the right one on the, this is the model temperature when you incorporate the latest land use, land cover, as well as latest urbanization morphology. So you get most close to observations in terms of temperature. Again, in terms of wind speeds, you could notice the default model actually overestimates winds drastically. But as you incorporate the morphology, you start getting most realistic wind speeds too. Even here, you notice that the observations and model go hand in hand in terms of wind speeds when you incorporate the urbanization as well as latest land use land cover. That happens even for ventilation coefficient. Ventilation coefficient indicates how much ventilation is happening in the model, and you see that the ventilation also gets more realistic. And all in all, what happens is your PM 2.5 simulated by the model gets improved and gets more close to observation. Here is an example. This was an event which occurred in Delhi back in November 2024, and you could notice that the observations show black lines, black boxes here, and the default model is a green and blue ones. But when you incorporate urban morphology, essentially your concentrations shoot up higher. So we have like higher likelihood of capturing the peaks when you have urban morphology put into place. So the idea is again PM 2.5 gets improved as shown here. Here is a special map showing improvement in PM 2.5 forecast by the model. So all in all, what's happening is schematic overview is because of urbanization, your winds are getting slower, your boundary layer heights are getting shallower, and because of which your PM 2.5 is staying within the close to the surface, and you have higher concentration, more close to observations. That is happening during daytime and nighttime. Also, you have uh, basically winds are lower and getting lower and lower, though boundary layer heights are slightly higher when you have urban morphology because of urban heating. But all in all, your ventilation is still low, and because of which you have higher tendency to capture the peak events. So these are two main this secondary organic aerosols, ensemble based probabilistic system, as well as urbanization. All these three things are going to be operational next winter. And with this, I would like to end my talk. And I would like to also mention that we have been in constant touch with the air pollution management authorities, like in Delhi, like in Mumbai, Pune, as well as some other states in India. So this is one of the review meeting that keeps happening every 6 months, and this is one of the meetings wherein the Commission for Air Quality Management looks at the models, looks at the performance, and suggests our improvements, and we keep on improving the model based on their suggestions. So there is some sort of dialogue started happening in India, and I would like to also underscore what mentioned by Professor Dr. Bhupesh, that we also have to increase on this sort of dialogues. So with this, I would like to end my talk. Thank you.
Okay, thank you so much, Dr. Gaurav Govardhan, who have, in a limit of time, was able to deliver a lot of information to us to learn much about what has been happening in the development of the air quality modeling capability to support the policy making. That is very, very important. And also, I noticed that there are just a few questions. I think many people are still thinking about the many parts. There is a very important question from Dr. Ramlal Verma about that why models are underestimating observations. I think this is general. If you can just answer just briefly at the moment, that would be great.
Okay, the quick answer to that would be A is that you have unrealistic meteorology in the model, very strong winds. B is that you have unrealistic emissions, because emissions are more or less outdated. We're going to have a latest emission inventory this year. So this work is going on currently on that. I guess these two are the most important aspects, and missing aerosol species. We have been seeing that secondary organic aerosols, so secondary aerosol in general are underestimated in the model. So that is something that we are working on. So I guess these are three quick answers to that.
Okay. Yes, that's a good answers. And also, I just want to ask maybe in follow up just a little bit that because I think it's very important also whether you have, I see that you have a lot of effort to really, run in and improve the emission as well in almost real time as much as possible. So would that be one of the, one of the underestimation if you don't have enough of the emission for the modeling, or what do you think?
Oh, yeah, that is a very interesting point, because dynamic emissions, that is something we are really trying to incorporate, especially for the sectors which show changes. For example, for traffic, if you could know that a particular area is heavily traffic affected, so you could probably put in, get the estimates of those. So that's something we would wish to work on, and depending on the data, if we get, I mean, of course, some work is going on that, and I guess that's something we should work on. You're right.
Okay, that's okay. Thank you very much. It's very interesting. I think many people still thinking about many parts of the presentation, and we will come back again with the question and answer. There is also a question and answer for Dr. Bhupesh Adhikari earlier, but let's come back to that later. And let me move on to the next speaker. Um, and the last speaker for today, in a very limit of time, he has already agreed, and actually already mentioned before by the previous presentation, that they have a very good collaboration to really share regarding the modeling work in northern India. So without wasting much time, already introduced that the Professor Pabir Patra is working mainly in Jamstec, and also a visiting researcher for RIHN in Kyoto in Japan. So let me pass on the microphone to Professor Pabir Patra to mention about the RRCAP project, which is a very encouraging project, has been completed. Let's see how it works and what's next. Thank you very much.
So you can see my slide and you can hear me?
Yes, certainly. It's full screen. Good. Yep.
Okay.
Please start.
Good.
Thank you very much.
Yeah, thank you, Vanessa, for asking me to give this talk. And then I'm also very pleased to speak now that we have seen what Bhupesh laid out, what we need for the region, and then Gaurav suddenly tells what has happened. It's a wonderful progress which has been happening in the area, and I think and so the opportunities are very clear that we have to do, and then there is skills in the region. Our project, which is started by Sachiko Hayashida from Nara Women's University, and she started the project around 2000 in a full scale, and ran the project for 5 years. And so the last 2 years of the project, 2023 and 3 to 5, I had to finish the project as the leader. And you know that our project started in 2020, so that it's just middle of the peak of COVID. So we could not do much observations. The things we are learning new things, but so then most of the modeling research also picked up in the last 2 years. Once we have observation from 2022. So my affiliations are already told, so I will move on to the talk directly. So as you have seen, maybe many of you know me, and then I work on greenhouse gases. So one sudden morning in Delhi, something happened in 2016, which drawn me into this air pollution research. Before that, I never worked on the air quality and air pollution things. So then we see in the news that Delhi become like a gas chamber, school won't open. And then so many of us follow cricket, and then in that time one of the high-profile cricket match was going on in India, Sri Lanka, and then there was abandoned, and the players started vomiting on the ground or some such things came up in the news. and they had to cancel the match. So then a lot of things happen, and then people come up with ideas that this is far field effect, including Iraq or Kuwait, Saudi Arabia, and then so many things came out in this news at that time, and so it's very confusing because I work on the atmospheric science. I do atmospheric science. The meteorology is common for everything. Plus, we know the region that obviously there is air pollution, but never happened such a thing. And then it becomes very confusing for me to think about it. So then I actually tried to get involved with some of the colleagues. We know Saulani was a PhD student that time with Rajesh Agnihotri, and then also NPL people joined in. And then we did this paper in 2019. So at the same time, Professor Hayasida was developing this REEN project. So I joined in because we have been doing other projects on the methane emission from rice field. So then I was like just participating in this thing. So REEN is Research Institute for Humanity and Nature. So the institute's idea is that how can the humanity and nature stay in the perfect harmony, and then we all live happily. So then there always the question is, what is the root cause, if anything, any disturbance you see in the system? So it's not about just the research, but what is the socioeconomic conditions, well, how that get us into this system, this kind of conditions. So that is like a, and as you have seen many news that the crop residue burning is one of the major highlight for the Delhi air pollutions in the October-November months. And there has been a lot of discussions, a lot of political outcome out of this, from this kind of discussions. But then our research is to know why it is. So then we looked at many various aspects in this. So we go back to fundamentals, like how do the rice cultivation first of all came to Punjab, and it was like through the Green Revolution in 1960s. So India had to come out of the famine in the drought conditions. So rice was introduced, and then obviously the multi-cropping system, but the climate of any regions permit certain things. Of course, the Punjab has been very rich in the soil quality, and then the very abundant in the groundwater. So all these things actually still promoted and rice cultivation, and exponentially in the 1960s and 70s. So by 80s, they are like a full-fledged rice cultivating state, and they have been supporting the government of India's whole public distribution system, like Punjab and Haryana, which they don't consume, but they give it to the country for the other people to use. So that has been very much backbone of India's self food sufficiency. And in 1980s, we achieved that. And then, so that by doing that, we also had to do like a mechanization, the high yielding varieties, so many and so forth. And then we, in the same things, many other issues come up. I will not go into details. Then the narrowing of the rice field processing time, and then the other things. So everything together. So our project looked at the three different sectors. One is the sustainable agriculture. And then working group 2, where I belong to, was in clean air. What is the cause of air pollution? How can you understand it? Then working group 3 is like a linking air pollution to the human health in the region. So anyway, I will not go into the details of the project, but just to tell you what we basically did. So I'll just show you very narrow part of working group 2, which is mostly the modeling aspect. Yeah, so Gaurav already showed this plot. So the idea to show this figure is that the blue dots on the map of India, you see there the CPCB's observation site in 2022. And our measurement sites are in blue dots on the right side, where Punjab, Haryana, Delhi, and Delhi NCR was focused. So we put the about 30 low cost sensors, which is we call QPG. So that's developed by Nakayama et al. In 2018, and this was overseen by Matsumi-san in terms of implementation and then running the instruments on field. And so what you notice is that the red on the Punjab in this map of India is that there's a fire hotspot count on an average, if you see in 1 year. But the CPCB sites mostly looked at the townships or cities, or the small town or small cities, and mainly Delhi is very densely observed. But the source region, which if you are thinking about the crop residue burning as a cause of Delhi air pollutions, the source region, which is like a rural Punjab, rural Haryana, was not covered in the measurement. So this is what the main focus of our study, to uniformly cover the whole region and see what we can get. And how did you do? So what did you do in this case? Then these other instruments are operating around the clock. And our intensive field campaign was from September to November, because we are focusing on crop residue burning. And we ran the instrument from 2022 to 2024, these 3 years. And what we did, that we get all the data locally collected in that in India, and then they're kept there anytime. The instrument measures like every 10 seconds, I think, one data. And then of course we make hourly mean and everything, and then we also look at fire count, how it has changed with time in the 3 months period in Punjab and Haryana. We look at the every site, how it has changed at the end. So this is for 2024 map, how every site has behaved over the last 3 years in this period, October to November period, and what the wind directions were from, where the fire counts were there, and then how it changed from 3 different years. And we try to look at these plots every day and update them, and we can share it online. We can give it to anybody else who wants it. And then also we look at this kind of plot which Matsumi-sensei innovated, is that why don't you show each data sets as a dot on the map, and show it by size, how much is the PM 2.5 concentration. So this is the kind of things you see on the map. And on the background, you also see that it becomes sometimes black, which is a high fire counts, and sometimes also become blue, there is shade, which means there is rainfall. So when the rainfall comes, the PM 2.5 concentration washed away, and it's very small amount, very clean conditions. It has helped a lot of time the government of India to be on the safer, people of India to be in the clean conditions. Sometimes they really helped. So if the rain comes, we clean up the things. We can see them very clearly from our observation and from what we get from meteorological analysis. So we don't have to do very detailed modeling to just see it, how it is happening and what are the controls. And then second thing that we, of course, we need to develop models, because without models we cannot understand what is happening. So one of the very simple model was developed fast immediately, was the Jamstick Takigawa-san. He developed this model. So what he did, you can actually do a full emission inventory from the fire hotspot. But you can also do a very quick, which is like a GFAS does in the global fire analysis system, is that you can just take the fire identity power and then the emission factor for PM2.5, or it can be any gas, and then there is a factorizations, and you can get the PM2.5 emission. And then you put that on the map in the model. And then you do just only PM 2.5 simulations. Then you can obviously do very simple in the method that you just wash out and other things. And what you come up with this kind of animation, where you run a model for like 18 hours, so it's called reanalysis, and you run it further for 72 hours as a forecast mode. So that same emissions which you emitted the last day, it's actually getting PM 2.5 concentration, and it becomes forecasted with the time. And you can look at these maps every day. You can produce these things every day. And that's what's interesting, is that, so of course we blame Punjab to Delhi straight away, but the emission does not go straight every day. They go in different directions. They go in almost 365, and then sometimes go to Rajasthan and then come back to Delhi. So all sorts of things we could actually analyze. So if you notice, our network also changes sometimes with year, because we see that some of the emissions to Rajasthan is escaping through the southern Punjab. So we sometimes move sites. So we adjust these things, because having so many sites, that's the advantage. You can look exactly where the thing's going. Are you able to capture everything? Are you able to missing some? Can you do better? So we can dynamically adjust such things. And so then this is one of the our very quick analysis. Then at the same time, as I mentioned, the clean air is a part of our project, right? It's a working group too. So modeling system has to be developed in full-fledged and to be tested, so that we can provide a useful forecast. Gaurav has already covered it very well, and then I just show you that we have, and then Bhupesh mentioned the mixed Asia, in the East Asia thing. So these models have been part of the mixed Asia. So they run it for the East Asia, but the same model is been now set up for the South Asia. Just move the domain and analyze to start with. So we said this is one of the example, which is a JMA's regional model system, which is non-hydrostatic model, NHM-KM they call it. It's developed by Mizuo Kajino in MRI, Meteorological Research Institute. The domain is like a 30 kilometer, and then inner domain is 6 kilometers. So analysis which I saw here is from 6 kilometer model, 6 kilometer domain, and you can see that he also, so again we are using QPG instrument, which is like a cheaper sensor and the low cost sensor. Then CPCB, so then he separated two different site categories. CPCB, let's take it on the left column, and then QPG, let's take on the right column, and see how it differs from Punjab, Haryana to Delhi. And what he finds is that, of course, the CPCB instruments and the model do very well for Punjab and Haryana and for to some extent Delhi. But when you move to QPG instrument, the model fails because the Punjab area emissions, I think, are not properly put, because sometimes we miss the fire count, sometimes we underestimate how much biomass is burned, how much emission is happening. I mean, all sorts of things. That is the idea of this modeling system. And he actually went on to do like a optimization of the fluxes. So the paper is discussing a lot about it, how to optimize, and they estimate the emissions from different parts of the Punjab and Haryana, so that you can simulate the concentrations. So it's very nice that, but the one thing we have clearly also seen here, that models are underestimate from Delhi, and we are not doing any assimilation, sophisticated modeling like Gaurav said, sold. But we can also see that QPG brings new information from Punjab and Haryana. So that was the very interesting analysis for us. And then detailed analysis you can see for the emission optimization in the paper. Secondly, we know that there are cases, also Gaurav mentioned that we don't do the secondary emissions very well, secondary SOA, secondary organic aerosols very well. But CMAC, which also the model being now tested in their system, we use it here because Yamaji-san in Kobe University, and so he does this modeling for mixed ACI and everything else. And see here in the model for this domain, again for India. And we use these model simulations in the paper, where we discuss a lot about the concentrations observations and the quality of them, and then how that also supports the GRAP things, what the CAQM does with IITM collaboration. So it was really helpful for us to use this observation-based analysis to see what we can say. And so here in these plots, we actually grouped it into 4 different regions: North Punjab, Southwest Punjab, and Haryana and Delhi. And here, so that black line is the mean concentrations, and then error bar is between the stations daily average differences, variations, and the blue line is the control model simulations. And we got a hint from the NHM-KM simulation is that the emissions would be like maybe about 8 times for crop residue burning, if you want to match the concentrations, given our modeling setup. Of course, model uncertainties has been discussed, and then given the model uncertainties, we need about 8 times more CRB emissions to fit the model in the NHM-KM model. But now we put that 8 times more emissions from crop residue burning in Punjab in the model CAQM, CMAC model. Then what you see that the Punjab concentrations, the Southwest Punjab concentration can be fairly modeled for the crop residue period, like middle of October to middle of November, which is a peak period of the crop residue burning. You do some part of North Punjab, which is like Amritsar and that area, and but then latter half we don't do very well, even after putting 8 times more crop residue burning, because the crop residue burning is not happening in the latter time in this part. For Haryana, which is more like a downwind, so we actually get one peak rightly and then one peak kind of misplaced, but not so much increase in the baseline of the PM 2.5 in Haryana. And now we go to Delhi, so the effect is very, very small. So even if you increase the crop residue burning 8 times, we don't really produce the baseline concentration of PM 2.5 in Delhi. So, which means that it has to be local emissions, it has to be locally generated in PM 2.5. And that propagation we could actually see in this kind of system. And then, of course, the WRCAP is a very common tools. So I think that must be used in some sense. And we had a dedicated person employed in our project to work on this. So then we didn't bring the model at like run at 9 by 9 kilometer for the domain and see the results more clear, and then here you of course talked about different categories of the emissions, and you can quantify them and switch off, switch on, such kind of things. And we thought we should test, you should use this as a some policy driven analysis. At the same time, the newspaper keep coming out of the, and also we saw it like analyzing the fire counts every day and keep adding them cumulatively for the month, for this years. We see that the fire counts, which is shown as a red to yellow, means low, red means very high. It's actually from Punjab, it's going down and down. It's very systematically gone down like any other part of the Indo-Gangetic plain, which means that basically no fire counts have been detected by Modi's kind of VIRS and Modi's kind of sensor in this 2022. So what is happening? Can we validate or invalidate these observations we see from satellite, and which is basically primary driver of the emission inventory things? And we also have here heard that the government implemented very strict rule. Even the people from the government level, commissioners are on the field to track and catch the who are not obeying the rule of non-biomass burning, non-crop residue burning policy. And so that must have affected this picture somehow. So we thought so. Then then that is our satellite picture. Then we are on the surface. We are making measurements continuously, every hour, every second. So then you can now see Bhatinda on the left side, the time series, the PM 2.5. Red is for 2024, and light yellow is like for 2023. And for also on the right side, you have 2023 and blue, and then 2 and 3 and 4. All sorts of things. Now you see that the PM 2.5 concentration in Bhatinda, which is southern Punjab, is not lower than 2023, but there are no fire hotspots in 2024. Same thing in Haryana, we see that the PM 2.5 obviously kept low until some very long time, and at about middle of November, but it suddenly then burst into very high PM 2.5 concentration, which means that maybe the policy the implementation by the government was like restricting people to burn to some extent, but then they suddenly found a way to escape the scene of being caught. So then we have model. Then again, model can help really policy, as it's mentioned already. So then what you can do is, okay, we have a WRF emission profile, which is like a peaking in the daytime around 2 p.m. Local time. And then now we can have an emission profile, which is like, let's say people are burning in the night or evening, let's say when there is no satellite overpass over our country. Then we can move it to like 6 p.m. So we did two simulations in this case. And we can now look at the concentration. So the bottom row here is the surface map, surface PM 2.5 concentration map. And the top row, it's a vertical cross section, which is height versus the latitude, longitude, like along the white line in below panel. So we are cutting across Punjab to Delhi and seeing what the profile looks like. Then on the left column is control simulation, on the right column is evening biomass burning. So in all the time you see that the PM 2.5 accumulation near the surface, whether in the vertical cross section or near the surface, at the surface, is always higher when you emit the PM 2.5 in the night. That's because the ventilation is so low in the night that it get trapped and it stays longer, like 12 hours, for example. You see, emit at 6 p.m., it stays until 6 a.m. So you actually produce more PM 2.5, and then it ventilates slowly in the next day, so that you are not able to escape very quickly. But if you burn the crop residue at the midday, if the PBL is very high, like maybe 1-2 kilometers, then it will mix up and goes faster. It will wash away to long distances. So you have a wider effect, but less intense. So what you see in this case is the shorter effect, but more intense in the evening burning case. And then what can you, it's very difficult because we don't have a satellite, we don't have a measurement system which can tell when the emissions are happening. So what you can do, which you normally don't look at, is the diurnal cycle. Because you have a continuous observations, and diurnal cycle is one of the key underused parameter, I would say, that to model emission analysis. So this is what we did in this case. So you see in the left panel is a QPG observed concentrations, and the diurnal cycle is for the October-November time, the 1 month in the middle of October to middle of November. So no, it's a 1 to 15 November. Sorry, the first half of November. So what you see in this case is and then we have many lines. So don't look. And I think it's very difficult to explain all the things and also to study here. So let me take you through this main messages from here. So the green line at the bottom you see in this case is the Chandigarh data. So then the model actually simulates. So if you see the control model simulation, it's kind of the same level. It simulates well. There is an evening peak. You see it here. You see it in the 2023 and like that. So it's kind of not quite good, I think I would say. But now look at Punjab in 2024. The PM 2.5 concentration in the night is very, very high. It's like 400 microgram. And it's for the 15 days period average. It's not 1 day, 15 days average. So if people are sleeping at 500 microgram every night, if you don't have air conditioner or if you're opening your windows. So then model is actually really underestimating. It's less than half in the concentration, but it has a feature of the diurnal cycle when you move to the evening biomass burning. But in the daytime, when you emit the emissions in the midday, you have no diurnal cycle. It's flat because emissions have already escaped, as you see in the midday low value. And these are local hours, right? So then what you can see now that in 2022, when the fire counts are slightly higher, the PM 2.5 profile looks very similar diurnal cycle as we observed in 2024. Even it is lower than that. So even if you consider the model uncertainties, then your your emissions from the biomass burning should be actually higher, suddenly much higher, maybe twice or thrice as you can emit. And it will be a 2022 comparison. So what you saw, the flat biomass burning profile distribution on the hotspots from satellite is kind of not valid. And second, and the final thing I want to highlight from this plot is that now Delhi is a black line in these plots. And Delhi PM 2.5 diurnal cycle profile is actually very high. It's a sustained evening profile in the even elevation of PM 2.5. And then it goes down in the daytime. So which means it also shows very similar profile what you would expect if you like have a constant emissions in this location. Because in the case of Punjab, the PM 2.5 increase in the evening and then it actually goes down and like that. But for Delhi, it's much more flat. And only you see that the ventilation in the daytime when the PVL is slightly oil mixed. So it's a kind of constant emissions from the city behavior is apparent from these plots. And our model is always very, very underestimating. So model is always at the half or even 1/3 level. So without assimilations, we cannot get to the concentration. But then we did not do assimilation because we have a short time, 2 years time period for analysis, and maybe 1 year for the postdoc to write a paper. But then even if we assimilate, our process level understanding of the emission amount is lacking. So that's what is the main message from this. And then Delhi has to solve its own problem. And our project goal was to quantify how much is the effect of the Punjab biomass burning on Delhi air pollution. So we do the quantification map bar chart. So it's like again for 4 regions we have been already discussing: North, Southwest Punjab, and Haryana and Delhi. And this orange bar part of the orange part of the bar is the crop residue burning contribution. Obviously, Southwest Punjab is highest. And Delhi is about 18 to 16%, depending on how you believe the emissions. But I think 2022 may be correct. But then 2023 and 4, I think, is underestimated. And then, as I mentioned, that 2024 is not acceptable because of the fire hotspot. What you saw are kind of misleading to the what concentration we have measured at the surface. So the uniform observations was the key part of this analysis, observation-based analysis, and what conclusion we have arrived at so far in the RRCAP project. Yeah, so and then with that, I think I should just conclude so that we can always come back to discussions. That RRCAP project has performed continuous measurements in the 30 sites in the Northwest India, and we are focusing on the crop residue burning period and 3 years. So we could actually establish capability, like we can actually distribute this data in the real time. We actually distributed in given the access to the CAQM for final year, these data sets, and then the our analysis system. Every day they could check if they wanted. And then we can confirm the weak role of emissions of capacity burning on Delhi PM 2.5 concentration. This is still a kind of, I think that that's why people have been arguing, like if the capacity burning has gone down, but Delhi PM 2.5 and it doesn't go down, but then Delhi PM 2.5 concentration remains high, even though capacity burning completely finished when the wheat is already cultivated or sown. So we have used 3 independent models to study that Delhi high PM 2.5 concentration primarily due to local emissions, not far field, Delhi NCR. And then model sensitivity simulations are great tool to visualize the policy implications. So what I'm saying by this last point is that if government of India or the policymakers goes to say that, okay, stop crop residue burning, but then you don't have the full tools to control like what is happening the hour to hour. But this can be already put into the model and say what if the people do in different timing of burning to escape the satellite. So you could actually run a model and say that no, don't burn in the night time. Even if you want to burn in the daytime, but in a small amount. But then we cannot implement such a drastic policy because the cropping system of Punjab or Haryana or any place has been developed over the hundreds of years or at least more than a few decades. So they cannot be suddenly changed. So you want to make a policy which is like a well communicated with time and stepwise action. Let's say you decrease every year 10%. Then you provide the infrastructure, develop infrastructure over 10 years, and then you control it. Not one day that, okay, stop zero burning, because that will not affect positively to your system. It is affecting negatively into the system, and it actually produce worst global air pollution in your region. Finally, thanks to my modelers, the modeling team, and then they really worked hard and produced this result. So I could show you today. I think with that, I'll end my talk. Thank you very much.
Okay, thank you very much, Professor Pabir Bhadra. It's very interesting project that has trying to link up, with the ground actual data and modeling parts that I noticed that, a great team out there in Japan who has been working hard regarding behind the modeling part as well in Jamstack itself. And so there are quite a few questions. Actually, a particular question for, I think for this last presentation is from Dr. Ramlal Verma talking about farmers and escaping satellite movement. You already mentioned a little bit, right, that the biomass burning farmers are getting smarter by somehow changing the activity. And I don't know if anybody have a particular question for this one, but I just have got a little bit of a question, if I may ask, that for when you identify that the crop residue burning is not that the first priority to affecting the city of Delhi air pollution. So do you think this fact will affect any change in policy or not?
I hope it does, because but again, I mean, so very fundamentally that so Gaurav also touched upon that. So if you use the concentration from that region and assimilate, you of course affect this one. But the problem of our modeling system is that unless you properly simulate the whole regional PM 2.5 concentration, the gradients are not set up properly. For example, if what I mean to say, in atmospheric transport, it's only a gradient which matters. If you have a constant concentration all through the place, there will be no movement from emission concentrations from one place to another. So if your Delhi emission concentration is lower, And if you have high in the Punjab, obviously your model will bring it from Punjab to Delhi. But our model always showing the Delhi concentrations are very low in the model, which means that you will also bring a biased transport because your concentrations are low in Delhi. So anything from boundary will come in. So I think those are also very difficult problem to tackle for us to as a modelers. I think model has to develop to by a process based model itself will produce a kind of a the distributions roughly okay. Then you assimilate, that will be helpful. But then if you just assimilate the concentration and increase your concentration at certain places, it will not help very good, very well to conclude the contributions. So by saying that, why I mean that if you look at the AOD from satellites, Delhi will always show you high concentration, but AOD over Punjab will be always very low. What you see from the surface concentration is a very different story. So in the very high crop residue time, Punjab gets very high, but Delhi remains low. But if you satellite picture, it will not be the same from AOD if you look at. So they're very misleading. They have been very misleading to us in many ways when you look at the just data. So model has helped to some extent to quantify. Then, for example, we increase the PM 2.5 in Punjab area emission from crop residue by 8 times. Still, it did not affected much to Delhi concentrations. So those are the kind of key points which came out. So policymakers has to listen to it, I think, in some way, if they want to listen. We cannot force because we are not in a government contracted system. So we cannot real. But I have spoken to CAQM. I have gone to their offices. I have gone to many think tank in Delhi, two of them at least, CEW and then CSE. There are two big think tank on the air pollutions. So I have gone and personally spoken to them. I think somebody has heard about these things, and let's hope that something will happen. And what I want people to listen is that we need observations, like I already stressed before. We need observations to be able to understand the system of the air pollutions and the dynamics. Yeah.
Okay, thank you so much. Yes, there can be a lot of more discussion. And I think at this point, I would like to bring everyone into a very short time for discussion and Q&A also. And in particular that I noticed the question, but not in Q&A, but the first one in the chat box that talking about the presentation of Dr. Bhupesh Adhikari. And asking about, can you please give us some example in the context of Nepal, how the modeling results were used to evidence-based policy making. So Bhupesh is still there?
Sure. Yeah.
Would you like to say something about this point?
Sure. Thanks. I mean,
yeah, please.
very important question. But like I alluded to in my talk, the amount of policy influence that modeling-based studies need to do haven't happened that much. But if you look at, say, Prabir's presentation or Baru's presentation, similar to that in Nepal, when we've run the model, the long-range transport of air pollution, how pollution is coming from elsewhere, and the contributions from the local sources versus regional sources. These are all insights that have come in the policy arena based on models, because your observations alone cannot really tell you. You see a spike in Delhi, where did it come from, right? So, I mean, things like this, the information that feeds into policy, a lot of it has come from model, because models are able to synthesize what we're observing. And so any interpretation or like in-depth interpretation, we always use some sort of model to explain the observed behavior, right? And so my point precisely is, I cannot give you a list of 100 things that have happened because of the model studies in Nepal, or I mean, India is a separate special case, because there's a lot of things that are happening in India, and you saw all the detailed modeling that IITM is doing, but that's only in India. If you look at what's happening elsewhere in the Hindu Kush Himalaya, starting from Afghanistan, Pakistan, Nepal, Bhutan, Bangladesh, we're nowhere close to what is being presented by both Prabir and Gaurav. And it's not only like, so, I mean, again, this is where we could be. And then my whole take on today's presentation is building capacity. And we've been talking about building capacity, like I said, even for the Malé Declaration. My last talk for this project was in 2017, and I was raising similar issues there. And again, we have long ways to go, partly because, again, there are bigger challenges than technical and challenges, I feel.
Okay, thank you
But
so
I mean,
much.
to answer in short,
Okay.
any interpretation of observations, in depth, both on regional scale or where is it coming from, or why certain processes are observed the way it is. In behind the scenes, we are using some sort of model to explain that.
Okay, that's great. It's a starter of the discussion that, as you already noticed, that we want to talk more about this later on as well. There is a very limited of time, but I just want to quickly, if anyone can answer in Q&A question regarding the there's a particular question actually to Dr. Sachin Goude team about the extreme PM2.5 spikes always require compound transboundary smoke and local stagnation? If so, do your models use meteorological thresholds as a warning trigger, for final concentration? If you could answer that. Yeah, go on.
Yeah, it's a very interesting question. Models tend to overestimate the meteorology. So you have stronger winds in the model that causes a lot of problem, first thing. Second thing, that sort of a cue we get, especially during winter, that is during December and January, what we have found is whenever you have reversal of winds in Delhi, that is when you have a visit of western disturbances visiting Punjab, Haryana, and Delhi, you get the reversal of winds, and because of which what happens is while the winds reverse, they become zero at a particular time, and it is when you have this sharp spikes happening. So if a western disturbance is approaching Punjab or Delhi, we do get a queue there. But if it rains, the concentration will dip down. If it does not rain, the concentration will hike. So there is a queue, but you have to take it with a pinch of salt, I would say.
Okay, thank you so much. Yeah, I hope that explained. For the question, and just one last one. Talk about the why choose Wolf Kim. I think a number of our researchers here use Wolf Kim instead of other chemical transport models. Well, I think anyone, if you could answer this one, or I would guess this one. If I could say also that instead of Chimera or Geochem, WolfChem is open, right? Open in a way for anyone to try or to download. But of course, I don't know any particular reasons for maybe a Pabir with you.
Yeah, so
but you use different models, yeah.
Yeah, we use three models. One is the NSM-KM, which is a Japanese and own model, and then WarpChem, and obviously easy to download and run because they have optimized the processing systems quite nicely. And Warp and then CMAC. CMAC is a bit challenging to prepare emissions, as I understand. But once you know, this is a nice model because you can put many things like what Gaurav was saying. You can do many ensembles, so it's very quick. So I think that why WAP can become popular, I think that also the integrated meteorology and chemistry, because sometimes that these two things feeds back, because particularly the aerosol, the radiation schemes feeds back to the meteorological scheme. I think that really I like it because I always use AGCM in our global models. I don't like CTMs because CTMs are like a 6-hourly run by 6-hourly reanalysis field, which is not enough to resolve the boundary layer progression in a day, for example. So many things I think in WarpChem is done consistently. So that also become a good reason to use WarpChem. But then chemistry is a big problem, like what Gaurav was mentioning. Yeah, we need a much detailed chemistry because secondary organic aerosols are almost sometimes 50% in any system, any place. So if you come to Japan, it's actually organics are much bigger because the anthropogenic emissions have become much lower because they control it. And it can be much bigger than the even anthropogenic component of the aerosols. So then, but organics are not always modeled well, modeled at all. So then that's a problem sometimes. So
Okay.
WarpChem also has to come up. CMAC can help, but in our case, all three models give us similar results, which is good. A systematic underestimation.
Okay. And maybe it comes to the point that Bhupesh mentioned about the model in comparison in the future. I don't know. It's going to be something we can think about as well. But in any case, there's another question, but we are running out of time. I'm so sorry that I could not keep everyone. But of course, emission inventory isn't a big question. Certainly, I think this information can be replied if you can reply quickly, or if you want to reply directly to the person who asked. Emission inventory, which one is used? I think it's a combination that has been shown, right? But in any case, we will share just to relate to the specific question that has been mentioned, that if we can share, if the speakers, I think only Professor Prabir share me your presentation. So if you, Dr. Gaurav and Bhupesh also can share your presentation, the one that you think it can be shared to all the participants, that will be great, and so that they can get all the answers as well. And now just to very last, and so sorry about that, I have to move on to Professor Kimon to give her final remarks, closing remarks for us. Very rightly. Thank you so much, and please, Professor Kimon, can I pass on the microphone?
Thank you very much. Good afternoon from here, from Bangkok. So thank you, the organizer, for giving me this chance to give concluding remarks. I try to make it within 3 minutes, not 10 minutes, so that you feel free. So first I would like to congratulate RRCAP for launching this series of seminars covering very important topic in air quality management within the regional scope that relevant for Malé Declaration region. And I also would like to thank speakers on a very good presentation, very informative. And that gives us a feeling that there's some very good modeling capacity already exists in the region, right? And want to congratulate Ishimot, IITM, Jamstex, Akash for pioneering this work in South Asia. And we know that air pollution knows no border. Everybody like talk about that. Pollutants released in one location, it takes a couple of weeks to circulate the globe. So that's why the modeling tools become so important to track the dispersion, transport, and to apportion where what come from. Like the last presentation mentioned about crop residue urban burning and the impact on daily PM2.5. So that is one of the evidence to show how we limit the policymakers. So that's why in the air quality management framework, the first question everybody asks, why pollution so high? Where it come from? It come from my urban area or from the local, but regional, but domestic, or come from other countries? And once we answer that question, we know what to do, what pollution to control. And then it also stimulates like regional cooperation to deal with the issues in airshape management, right? And we talk about airshape, that's very important thing. So modeling, as we can see, also help us to deal with, like, to simulate some what if scenario for policy recommendation. So as mentioned, and also a vision from the presentation, there are recent trends to incorporate AI, machine learning, deep learning to improve accuracy and air quality forecasting. Because we know that traditional modeling, like we need boundary condition, that is hourly, with a lot of uncertainty, we need hourly emission when we never have. Because near real-time emission also never that time. That's why we don't have really the modeling design to fit precisely, never precisely, but appropriately to the monitoring designs. So that's why the new model with fusion of the observation data, like satellite data and local sensor data, as mentioned in IITM case, so we help to improve accuracy. But we remember one thing: the deep learning needs big data sets with good quality because we train the artificial neural network and we need to have good data to train them. So, as I mentioned in AIT, like in my center, we're focusing on Southeast Asia. We also do air quality modeling, and then we also do early warning, mainly focus on the like open burning, forest fire in northern part of Southeast Asia. And I'm also learning from your presentation. That is very good for that. Then there's, as we mentioned, there's good modeling capacity in Malé Declaration, but mainly by leading institutions. That is the point. So just want to note that we need close cooperation between the university, research institution, and policymakers, government. So only when we produce, researchers need to produce good data quality in order to win the trust with the policymaker, because they need to trust our results. And only when we work close to each other, we can use our modeling design or whatever technical tool, emission inventory, monitoring, to use effectively for air quality management at urban scale, regional scale, country scale, and Malay Declaration scale, or Southeast Asian scale. So then we also need to learn from each other. And this is very good chance for all the scientists sitting here, I think, to listen, to learn from your presentation. And with that, I would like to thank you. Thank you, organizers. Thank you, speakers. Thank you for participants online. I hope that this seminar bring you to some good information. And I heard that they will share presentation, they will share the records. That would be very good. And please distribute those good information to your friend, to your colleague and network. Thank you again.
Okay, thank you so much, Professor Kimon. And this closing our webinar, I just want to draw your attention to the chat box again about that. We want to hear from you, okay? And about the webinar, we have the next in the series, so please do fill out the evaluation form. And I highly appreciate all the speakers today who have been, preparing and also sharing everything. Thank you, Professor Kimon, so much also to be giving us a bit of insights. Actually, a lot of that we need to discuss more, and South and Southeast Asia, of course, because, like I heard that in Malé Declaration, they also talk about the possibility of some impact from Southeast Asia and so and if any transport. So we will have the next webinar coming up at the last Monday of the month, next month. So many of the discussion here will continue, and we will focus even more on a monitoring part, which we have a lot of details. I highly appreciate all the modelers here that has been working hard, and also the whole of his team. And we will see you again, either as the speakers or instructors later on. The Malé Declaration is coming up in the revival activities this year and next as well. So we hope to hear from you in the evaluation, not only in the evaluation form, but also you can directly contact us, and you can also give us more suggestions of any particular training as well, because we will have a soon discussion among the Malé Declaration countries in South Asia to see what's next. As Dr. Bhupesh Adhikari mentioned about that, is many years back. Discussion has started, but where to go next? So we try to work it together. And thank you so much. And RRCAP, on behalf of RRCAP and RRCAP, the South Asian Cooperative Environment Program, we want to see you again. And I have a big applause to all of us, particularly the speakers and our closing. So thank you so much, and see you again